Yes, now it's okay.
Okay, thank you. And I would like to say thank you for invitations and also introduce me. And also today, I'm going to share a little bit about my experience about my research work in the titles of the high frequency weighted power transfer, or you can call the WPTs. And I come from Mongkut University of Technology, North Bangkok, Thailand. And you can see right here, and I have 3 points to talk today. The first one, introduction, and the second one, and theory and system design consideration. For today, I would like to focus on just the antenna design and also the antenna technique to improve the power transfer. And I will share you about the hours, the research work that I have done earlier. And for the introduction, let's see here. If you take a look at the picture here, and I think you're familiar about this technology because it's already integrated into your cell phone, for example, iPhones and Android phone, for example, Samsung, LG, something like that. It works by using the near field magnetic coupling, or sometimes we call the induction techniques. The induction technique is like a transformer. It works like a transformer. And this technology developed by the Weighted Power Consortiums, or the WPT, they launched the commercial standard. The name it is a QI or chip in the 2010s. The maximum power is around 5 watts, not greater than 5 watts, because I think, my opinions, they got some problems about the radiation problems and also EMI problems. And let's see, the frequency is just, they use around 100 and 200 kHz and very low frequency and also low power, 5 watt. And they try to develop more power, is around 120 watts, but not released yet. And the frequency a little bit go up. Maximum is around 300K. And for more detail, you can see the more detail in the website, weighted-power-consortium.com below. And the next one, okay, let's see. Let's go back to the theory behind the technologies. Let's go back to the Tesla power transfer experiment in the year 1890. They try to show you how to transmit power from the TX antenna and go to the I antenna via the air. They try to show the possibility of the power transfer, and they have the power transmitting powers P and receiving power S, primary and secondary. The concept is like a transformer. They connect the power supply, AC power supply, to the primary coil, and then they show the possibility of the power transfer, and then supply the power to the lamp light. If you did phenomenon, you can explain all this phenomenon by using the Ampere law and Faraday law below. You can see if we have the current flow on the Y, and then the current here, the magnetic field, if you have the receiving coil, and the magnetic field caught the receiving coil, and you get the voltage by using the Faraday law, something like that. And if you want to take a look at the magnetic field distribution, you can try by using the simulator. For example, ANSYS, System Microwave Studio, FSS, or something like that. So many commercial software to predict the magnetic fields. You can see on the left-hand side, for example, I have a TX coil right here, and then you can generate by using the current flow around the coil. The magnetic field can be generated. You can see right here. And I would like to talk about a little bit the behavior of the magnetic field, the nature's property of the magnetic field a little bit. In the right-hand side picture right here, the magnetic field decay is really fast compared to the distance, inward proportional to the power to the third, you can see right here. The efficiency is maximum at the short range. For the middle range, a little bit low because the field is decay very fast, like an exponential. And the next one, the long range, the efficiency is very small, approach to zero. This is the first experimental by Tesla. And actually, we can devise the methods of the wave power transfer into three categories. The first one today, I want to talk about the magnetic inductions and also magnetic resonance coupling. That is the key today. And the magnetic induction and magnetic coupling, sometimes we call the near field techniques. But the second one, what we have the magnetic radiation method also. The magnetic radiation method, we have the microwave method, is verified by NASA experiments below here in this picture. The NASA used the big antenna, that is the parabolic reflector antenna, and transmit the microwave energy into the mountain. And the receiver is located at the mountain right here, and then they achieved some power at the receiver. And also the concept of the laser beam method is shown below right here. And the last one is really dangerous, that is electrical conduction. It's like a lightning phenomenon. Okay, if I would like to focus on the commercial application of the wave power transfers. Actually, we have two groups to develop the wave power transfer technology. The first group, that is the wave power consortium, or the BPC, that we know about this. And also we have the Power Matter Alliance, PMA, and also Alliance for the Wave Power, or HF WPT also. Two groups try to develop this technology. But the first group launched the standard named QI, and also the second group tried to launch the standard PMA and also license. The different things about two groups, it is the techniques. The first group, they use the magnetic induction. And the second group, they use also magnetic induction for the PMA standard, and also they use the magnetic resonance for the license standard. Difference in terms of the frequency also. Low frequency for the magnetic induction, and high frequency for the magnetic resonance. And also different in terms of the communications, and QI use ASK, and also for the reason use the Bluetooth technology. And the coupling is highly and also the direction, the power transfer distance, C direct distance for the magnetic induction is very low distance, lower than 5 millimeters, because this is a problem of the magnetic induction. You cannot move the receiving antenna out far away from the center of the transmitter. But the magnetic resonance is a little bit relaxed compared to the magnetic induction techniques. And also the power efficiency is very close together. And the maximum is the magnetic induction is around 80%, but the magnetic resonance is a bit low, 70%, due to the radiation loss or something like that. And the member supports the technology, you can see below. Let's go to the next. For this slide, I would like to talk about a little bit about the drawbacks of the QI or chip technology, because the chip technology is based on the magnetic inductions. And for this case, the magnetic induction needs the perfect alignment between the TX and IX antenna. If you go back to the limitation of the C distance, you can see right here, the magnetic induction is very small distance, you can see. These are the big problems. You cannot move a little bit. TX and IX antenna should be perfect alignment together. And another one that is an interference or EMI problem, because the magnetic field generates so much the noise and can be disturbed another circuit. That is a big problem also. And this is the reason, my opinion, this is the reason why we limit 5 watt right now. And if you want to take a look at the limitation of the power, radiation power, you can see the standard right here, Ignat, Avanza, on also the activity standard. Okay. For the next one today, I would like to focus on the technique that we call the magnetic resonance coupling. The magnetic resonance coupling, we try to use this method because we try to increase more the distance, power transfer distance, and also we try to solve the TX and RX antenna misalignment problem. These are big things that why we need magnetic resonance techniques. These are comparisons between two methods. The first one, magnetic resonance, and the second one, and the magnetic induction. Magnetic induction is the left-hand side, and the right-hand side is almost the circuit components, and the block diagram is almost the same, but different in terms of the capacitors. You can see left-hand side, the magnetic induction. We don't have the capacitor at the antenna, and we use the very low frequency in terms of kilohertz. And for the magnetic resonance, the frequency a little bit go up, higher in terms of the megahertz. And the magnetic resonance, we insert the capacitor in the TX and RX antenna right here. It's like a resonator circuit. These are different things between two methods. And the distance a little bit more relaxed compared to the first one. This is the same thing that I already talked about this. For the left-hand side, magnetic inductions, the behaviors is like a transformers, no capacitors. And you can see the right-hand side with a picture here and the right-hand side picture here. That is the magnetic resonance technique. You can see the magnetic resonance, the distance can be a little bit more compared to the left-hand side, and the misalignment can be possible. It is possible to do that. It is the overview of the system design. What we have the power supply, and we have the transmitter. Today, I want to talk about a little bit the transmitter also in the maybe later. And also the next one, the antenna here, TX and RX antenna right here. The next one, receivers. And also we have the load here. Because the load is very important, because the impedance of the load affect to the whole the whole system. And also let's see here. Okay, today I would like to focus on the TX and the RX antenna system. Yeah. If you want to try to simulate the TX and RX antenna, you can start by using the commercial software, and then you just choose the basic antenna coil right here. We have TX coil, and we have the RX coil right here. You can choose the materials such as the copper or the brass or something like that. And then first you have to simulate to find the inductance value first, right here, L. And let's calculate the capacitor value. After you get the capacitance, you put here again, and then let's try to simulate, and let's see the final results. You can see right-hand side, that is the magnetic field distributions. You can see the magnetic field distribution, the power is already exchanged between TX and RX antenna under the conditions of the resonance conditions. Okay, you have to match the capacitors into the TX and RX antenna to get the strong magnetic field between two antenna. Here, for example, before I go to the details and parameter consideration, I want to talk a little bit about the ratio of the TX and RX antenna, because this is very important parameters. And you can see the right-hand side, that is the graph of the efficiency of the system, and depends on the ratios, side ratio between TX and RX antenna size. The left-hand side, the TX antenna size is around D, and the RX antenna size is around D sub 2. If you choose the same configuration, same size, you got the maximum power transfer at the near field regions right here. You can see right here. If you choose different size, you can see 1, 0.3, 0.1, the power efficiency, the maximum power efficiency is go down, go down. This is the basic property that you have to know about this before deciding the antenna. And also the horizontal line, that is the distance normalized to the D. Okay, the maximum distance, the effective distance is around 1. The normalized distance is around 1. That means the distance is around equal to 1D diameters of the TX and IX antenna, for example. The next one, okay, I already talked about the TX and IX antenna. It's like a resonator circuit, but resonator circuit, the property of the resonance depends on the Q factors. What is the Q factors? Q factor is the maximum energy storage divided by the power loss. What is the power loss? Power loss is generated from the resistance of the coil. Resistance of the coil right here. And if you minimize the resistance of the coil, and then you get big Q. Big Q means more power transfers compared to the low Q. High Q better than low Q for this theory. And you can see what is the R coil. R coil depends on, consists of the N turns of the Y, and also A. A is the radius of the loop antenna. And what about the B? The B is the Y diameter. And also multiplied by RS. RS is the surface impedance of the conductors, depend on the material. For example, gold, silver, and also copper, something like that. It's a little bit effect to the size. And also the next one, RP is very important. RP ratio with the R naught. RP is the ohmic resistance due to the proximity effects. The proximity effect is created by two coils close together. You can see this picture. If we increase the N turns, Q is go down. If you increase the C parameters, C parameter is mean spacing between each turns, you can see right here, coil turn, and increase 3, you got big Q. And you increase the B diameter of the coil, of the Y, and then you got big Q also. And you can see this plot, the horizontal line, that is the spacing between coil turns, and you can see more distance, more spacing, low RP value, you can see right here. That is how to improve the quality factors of the resonators. The last one, R naught, it is equal to N and RS divided by 2 pi B also. And you have to minimize the R resistance of the coils as much as possible. That's the meaning. And I try to simulate for you right here. The left-hand side, spacing between the Y, every coil turns, and you can see if I increase the spacing, Q is increased also. You can see quality factor is increased, and resistance is decreased. Okay, and L is decreased also. If I change a little bit Y diameters from 2.9 millimeter to 12.7 millimeter, what you get? The quality factor is a little bit increased compared to the first case, but not too much. Okay, but not too much. You can see right here, 750 and 727 is a little bit changed. I try to summarize for you right here. You can, if you want to study the coil property, and you can try by change some parameter. For example, the distance, the spacing between coil turns and the size and the length, and then you can see the effects of these parameters. I want to conclude here. The turn of the Y increase, Q go down, and the spacing between coil, between the Y increase, Q is go up, and the B increase, Q is go up also. You have to keep maybe 2 times spacing compared to the Y diameters. I recommend you keep 2 times more. Okay, if you want to try to measurement the effects of the resonator, I mean the quality factors and power transfer, you can do by using the network analysis. The network analysis, you can measure 2-port networks, 2-port device. The antenna TX and IX antenna is like a 2-port device. You can do by using the network analysis. And you can do by the simulator, left-hand side, you can see right here. And we have TX coil, we have IX coil. After we find the capacitance value, we put into the simulator, and then you get the magnetic field distribution, and then you try to create some coil and then measure by using the network analyzer. You got the same things. I will show you right here. Okay, sorry, go back a little bit. The right-hand side pictures, it is a display of the network analyzer. You can see S21 right here referred to the power transfer between 2 coils, S21. I will talk later about the S parameters. Before I go to the details of the analytics, and you can see we have 2 techniques to feed or excite the coil. The first, it is the conventional direct feed techniques. What it means, you can connect directly from the TX circuit to the TX antenna, and you can connect the RX circuit to the RX antenna directly. But for this method, it's not, I think not good, because the impedance is changing really fast and not stable in terms of the impedance of the coil. But the second one is better, because the coupling feed techniques. We have the resonator coil right here, TX coil, and also we have the RX coil right here, the big coil, and we have the driving loop here, and we have the load loop here, and the impedance of the system is not changing too much and stable compared to the first one. The next one is theory. You can analyze the power transfer by using the network parameters, S parameters, because the TX and RX antenna can be represented by using the 2-port networks. And then for the measurement, it's very convenient, because right now we have the network analysis. We can measure the S parameter directly. And let's see what happens. It is the power transfer efficiency in terms of the S parameter. You can see the power transfer depends on the power to the load, delivered to the load, and divided by the power input. And the power transfer related to the S parameter also. The first one, that is a gamma input. And the second one, second terms, that is a S21 parameter. That is the big parameters. That is the key parameters of the power transfer. Because the gamma in normally is very small compared to the another parameters. And also gamma out, it is a big effect to the G sub P, or power transfer efficiency also. And you can see if the gamma in is very small, because we can control the impedance of the transmitters. And what happened? You can simplify both. You can see right here. It's just S21 square multiplied by the third term right here. And the third term related to the gamma S11 and S parameter, and also the gamma L also right here, depend on the load. The load impedance is very, very important for the power transfer designs. This, for example, also after we got the model for the simulation model, and we already simulate the coil, and then you can try to experiment by using the Y right here, and also you can calculate the L and the C by measure the L first by using the network analysis. The inductance get by using the network analysis. And then after you calculate, you get capacitance value and put the capacitor right here. And then let's try the result. Let's try to check the result right here. The left-hand side indicates of without capacitors, nothing. S21 is really small compared to the second picture right here. The capacitor is already at, and then you can see the S21 is very, very high compared to the first case. S21 refer to the power transfer efficiency, because if you go back, S21 is the key parameter here. You can see S21 is the big parameters. And for the next one, I would like to talk about the misalignment problems, because for the magnetic induction, we cannot move the antenna far from the center of the TX path because the nature of the magnetic fields decay very fast compared to the distance. And you can study this case by using the simulator, for example, CRT microwave stereo ANSYS or the FSS or something like that. And you can move the RX antenna in the X direction, for example. The right-hand side picture shows the result G in terms of the X parameters. After you move the RX antenna far away from the center of the TX antenna, you get the power transfer is a little bit go down. Okay, the effective area is around 3 centimeter or 3.5 centimeter. There is a limitation because the magnetic fields decay very fast, but the magnetic resonance techniques provide a little bit relax in terms of the misalignment. If you want to study, you can plot by using the contour plot in the left-hand side below here, the right-hand side below here. You can move the RX antenna around the TX antenna path, and then plot the G sub P, and then you get like a contour of the effective areas, something like that. The same things, you can try so many shapes, and you can change the TX and RX antenna configuration, and then you can plot the G sub P graph, something like that. And this topic, what I would like to talk about the power repeater technique, and also the dual feed configurations, and also multi-feed partner configuration also. This is my experience. I have done about the research about the power repeater and also the dual feed configuration antenna and multi-feed configuration antenna also. I would like to show you and share my experience. Why we need the power repeaters? Because you know that we got some problem about the misalignment. We cannot move antenna more. Okay, and then if you have the repeater path, something like that here, we can extend the power transfer range or effective area more than the single TX path. This is the concept of power repeaters. And take a look at my simulation. You can see what we have. We have TX circuit connect to the TX antenna. Here, left-hand side TX antenna. And also we have the power repeater coil. The power repeater coil, it is the same thing like a TX antenna. It's just a resonator circuit. And we have the coil, and we have the capacitor here. We have the second repeater coil, and we have the capacitor here. And the receiver is located here. And you can see the simulation result in the below here. You can see the magnetic field is very strong transfer from the TX to the RX antenna. And after we simulate, okay, and we plot the transfer power efficiency in terms of the S distance. Spacing S, it means spacing between two coils. You can see that repeater coil is didn't connect anything to the TX antenna. You can see right here. And also you can see we increase more and more spacing as what you get. The GP or the power transfer efficiency a little bit go down, but not too fast. Slow down, go down right here, and we can extend the length of the wireless power transference more than the first case. This is some experimental at my university. You can see we have the transmitter here, TX circuit, connect directly to the TX antenna here. And also we have first repeater without direct connection to the source. And also we have the second repeater here without direct connection to the source also. And we have the RX antenna and RX circuit here. We got some power at the LED light. Here's another example. We have the lamp light, table lamp lights right here. And TX antenna located here connect to the TX circuit connect to the TX antenna. And then the magnetic field transfer to the second coil and re-radiate back to the third coil and then receive by using the receiving antenna here. And these are, for example, of my work. We have the TX circuit right here and then connect to the TX antenna here. And this is the receiver. And also this is the repeaters, power repeaters, resonators. We transmit around 22 watts, but at the receivers, we got just 1 watt or something like that because the radiation loss is so much. These some applications of the power transfer repeaters. We apply the power repeaters to the HF WPT system. You can see right here. We already published the paper in the radio engineering. Sorry, because normally the leaders consist of the very small TX antenna right here, the left-hand side below right here. Okay, and we cannot change or modify the TX antenna because it's already integrated into the circuit already, into the ladder already. But sometimes we try to increase, we need to increase the communications area more than the single antenna. You can apply the power repeater by put some resonator circuit or power repeater circuit near very close to the TX antenna right here. And then you can change the magnetic field distribution because the magnetic field distribution depends on the antenna element. Okay, you can see left-hand side, you can see. If I move a little bit up, the magnetic distribution is a little bit changed. And also if I move very close together, okay, you get the big area of the magnetic fields, something like that. For this work, I use 5 resonators right here, or 5 power repeaters. Okay, we got the very wide communications area compared to the first one, that is the single TX antenna from the leader. You can see the color, blue light colors, and so many colors refer to the detectable areas. Okay, you can see it's very big compared to the first one. These are some applications of the power repeater because no need to connect, no need to modify the TX or leaders of the HF WPT leaders. And another things I want to share you about my experience, that is the dual feed configuration. Sometimes we try to increase the distance, power transfer distance, because the single antennas, the magnetic fields decay very fast. Let's see the left-hand side picture right here. Single antenna right here, after we simulate, we got the magnetic field distribution is so very short in terms of the distance. But we try to increase the distance between the power transfer distance by using two antenna and feed by the same phase. Okay, by using the same TX circuit, and we use the power dividers and feed together with the same phase, in phase, and you can change how often is possible to do that also. But if what happens if you feed with the same phase? Can see the simulation here, right hand side. The magnetic field is linked together between two coils, and the distance, the power transfer distance, is a little bit greater than the first case, a little bit extended. You can see the simulation result. Power transfer efficiency, we can see right here. And the maximum is around 70%, and the minimum is around 20% at the center. This is from the simulation. And also, after with simulations, I did the experiment a little bit. We have two versions. The first version is Pana version, and the second version is really big coil version. We use the same powers, around 22 watts. The left-hand side, we try to prove the concept by using the receiver here, and also transmitting antenna, left and right, feed with the same phase excitation. I use the power divider here, okay, same powers. And the second one, the bigger versions. We integrate the RX circuit at the iPad right here. And the distance between two TX antenna is around 1.8 meter, 1.8 meter. And we got around 5 and 10 watts. And we can charge the iPad at the center of the two TX antenna coil right here. This is my experience. And another things I want to talk about the multi-feed techniques. The multi-feed configuration, you can do 4 or 5 or 6 transmitter if you want to change the magnetic field distributions. Okay, you can see we have 4 antenna here, and we use the same transmitter, same power, 22 watts, and also we have 2 configurations. The first one is parallel configuration. The second one is like a U configurations. And we found that the magnetic field distributions around the area, it change depends on the antenna configuration and also the phase of the excitation phase. And you can change the phase, in phase or off phase, something like that. For the next one, I would like to talk about the oscillator. Power oscillators is very important because we try to keep the efficiency as much as possible. What we have so many class of the amplifiers, A class, B class, and switch mode class, something like that. And the efficiency depends on the class also, you can see. The A class, efficiency is so small, and for the B class, a little bit more than the A class, but the efficiency of the switch mode class is very, very high, up to 100%, something like that. We choose the E-class oscillators, E-class amplifiers and oscillators, because the circuit is really small compared to the power. Because efficiency is up to 90%, it's so very high. And you can see the footprint of the board circuit right here. And also we have high power version, also 60 watts, something like that. I recommend you use the E-card, it's really nice. The next one, a good thing about the E-card, because the E-card, we can control the power by control the voltage supply. You can see right here. If you change the power supply voltage, and the power output is also changed directly. Because the equations about how to design the E-class, the power out related to VCC squared directly. You can see right here, you can change the VCC and you can change the power output. The last one I want to talk about the receiving circuit. We have so many things, we have so many configurations. for the RF receiving circuit. Right here, you can choose the bit diode with the highly covering time diode, something like that. The efficiency is around 92%. You can see this table. You can choose the bridge capacitor configuration. You can choose the bridge inductors configuration, and you can choose the double voltage rectifiers. It's okay because it's very high the conversion efficiency, and you can choose the double current configuration also. For me, I prefer to use the bit configuration. It's very convenient for me. And this is some my experience about the receiver. The receiver we already integrate into the. This is just a demo. The cell phone and the tablet, something like that, and the lamplight or something like that. We have so many versions by using the magnetic resonance techniques. Oh, these are all of my talk today. Thank you very much. And if you have some questions, you can type or you can write down in the Q&A box. Thank you so much. Thank you.
Thank you, Professor. And for the audiences, if you have any questions, please feel free to type into the Q&A box. So here we have a question. What is your maximum frequency?
The maximum frequency for the for the WP standard, right now we use the 6.8 or something like that. Let's check. Megahertz. Because the magnetic resonance suitable, the suitable frequency is around megahertz.
Okay. And the second question is, in your class amplifier, is it single stage or multi-stage?
Just a single stage amplifiers, E-card amplifiers. Right?
Okay. So I see there's no more question, and thank you, Professor Kittisak. And let's welcome the next speaker, Desmond Tan from ANSYS.
Thank you so much, everybody.
Thank you.
Thank you.
Let me just share my. So you guys can hear me clearly.
Yes.
Hello? You guys can hear me clearly?
Yeah.
And
okay.
I can see your share screen as well.
Okay. Good morning. Thank you, Professor Kittisak, for the great theory and design on the WPT, which is wireless power transfer. All right. My name is Desmond. So I'm basically based in Singapore, and I'm actually the regional technical manager for ANSYS, right, basically. And I support almost whole Asia, especially in China, Taiwan, ASEAN, and also India, right? And I've been around for almost 21 years. All right, basically I started from Ensoft, and after which it was acquired by ANSYS in 2008. Okay, so now I'm myself is working from home since 2008, supporting ANSYS in all the electromagnetic tools. Of course, include some of the mechanicals and thermal and stress capability as well. Okay. Then let me just so basically I'm located in Singapore and support some of these major customers, enterprise customers, right? Customers like Intel, AMD, and so on. Okay. So let's talk about this solutions that we can provide for this wireless power transfer. Right. This is not a very new topic, right? Basically, this has been around for almost like 10, 15 years. Right. I started with this supporting customers, some of the mobile customers, right? Mobile player, as we know. Okay. Then also pretty much 10 years ago, we started with some of the EV applications, right? Electronics vehicle. And recently, it has been hot topics again because of the EV, right? Basically, so we are working a lot on this, right? Basically, is battery plus wireless power transfer and so on, right? So without further delay, let me just start my presentation. So basically, the agenda here is more on solutions, right? How ANSYS can provide some of our tools to actually simulate some of this methodology for wireless transfer, power transfer. Okay, so the first item, basically, I'm introduce some of this electromagnetic tools for WPT and coupling simulations between electromagnetics and electrical circuit, all right, in a single environment, all right, and also applications on wireless power transfer, all right, inductive type and magnetic resonance type. Okay, we will talk about this too today, all right. Some of the actually just one application. Actually, I can actually put everything together in one application and show you the full system simulation on WPT. So if we talk about wireless power transfer, right, there's a couple of methods, right? Electromagnetic inductions, magnetic resonance, microwave, right? So much about this. I think the two popular methodology would be electromagnetic inductions, right, and magnetic resonance, right? So we can differentiate them. Well, I like to use the layman term, like differentiate them between low frequency and high frequency. Okay, anything that in megahertz, right, we will consider as high frequency for this case now. Okay. But there's a map and there's a gray area between that. So I'll show you what is the map like. Okay. So this is the map that I can show you. Like, induction is basically based on efficiency, right? The transfer distance is going to be the gap of the transfer distance is going to be very small. And the induction type is more on an induction type. Okay. And it should be like 15 watts. And when you get transfer distance higher and induction type 50 watts will be more on the resonant type of methodology. Okay, we're not going to so much about microwave type. I know that Professor touched a bit about that, but we will actually work pretty much on domestic. All right, that means what we face every day, like our wireless charging for mobile phone and some of the domestic equipments that we have at home. Okay. So basically, in the layman term, right, what are the tools that we use on this application? This particular application is low frequency, which Maxwell that we have, and high frequency, which HF. Right. If you guys have used our tools before, you understand these two different simulation tools. But those that don't understand, it's okay. You just think about low frequency and high frequency. All right, and we have both tools to actually address this both applications. Okay. So for Maxwell, basically, to be simple, it's a low frequency field simulator. All right, the software actually separate magnetic and electric. That means that you solve magnetic for one solver, and you have to have the same models and solve in electric. So it's a separate solver. Okay, basically. Then it's more on time transient lump circuit elements, right? I'll show you in a better. I'll put up a better example to show you what is going on, right? So just go through what I have here now. Linear and non-linear material. Okay, so what are the applications for low frequency? There's a couple of them: motors, transformer, inductor, for power machines and inductive noises. Right, there are applications like EMI, EMC for conductive emissions. Right, these are all Maxwell applications. As for high frequency, right, basically we call it high frequency structure simulator, HFSS. It's a full wave solver, which means that you solve both magnetic and electric simultaneously. All right, so it's a full wave, and it's solved for distributed circuit, right, for S parameter, Z and Y metrics. It's only used for linear, right? Example that these are all passive structures that actually solve in HFSS and Maxwell. Okay. Of course, for high frequency, there's more wider applications that we can see now is antennas, transformer, inductor for noise and radiation noise and signal. So applications like 5G, 6G, high performance antennas, okay, EMI, EMC at high frequency. These are all the major applications for HFSS. All right, so between solver. So let's talk about resonant type of coupling, right? Basically, when you talk about resonant type of coupling using Maxwell, okay. So when you talk about this, right, we can extract out the Maxwell parasitic extraction using Maxwell and couple it into the circuit simulator for resonance, right? So that you can solve for your resonance. So there's a couple of things that we need to extract and put into the circuit base. And together with the circuit base, we can actually couple with the 3D model, right? Solver 3D model that's solved in HFSS or Maxwell, okay? So for magnetic, right, we are concerned about RL and M, right, the mutual, and electrostatic is the capacitive, right, basically, okay? These are the two different types. So for inductive type of coupling, right, we are talking about magnetic induction stuff, right? The principal physics behind is magnetic coupling. So the major part is magnetic, so we can use HFS. We can use Maxwell, all right, because it's the nominant is actually in the magnetic field. Okay, so we can use the low frequency Maxwell solver to actually extract out the coil or the coil inductance and all the stuff, right? So the resonance circuit is realized by the lump capacitance, right? Solving using the circuit simulator, okay? So let me just go into the type, which is resonant type. Again, but it's high frequency. So basically it's very straightforward. We just use HFSS, all right, to couple it and see the S parameters and extract out the cell capacitance, okay? Let me come up with some of this. Let me just show you some of this, one of these basic applications that we see here, right? The coupling simulations for electromagnetic and circuit. Right? This is the circuit, okay? Basically, what we can do, by extracting on this circuit, we have all these drivers, the supply and all that. It's more like, I think this will be more like a subsystem simulations. And we can actually couple with the 3D model. The 3D model that's solved in Maxwell or solved in HFSS, all right? So it depends on the frequency they're working on, right, basically. So this is the Maxwell example because it's induction, all right? So this is more like a coupled induction type of power transfer. So from there, you can extract out the models and key in all the parasitic that you require in the circuit, okay? Let me just show you step by step. So the first step, basically for this induction, right, these are induction methodology. So we are going to use Maxwell. So we can actually create a circuit inside the Maxwell, a lump element circuit. And from there, right, we can calculate your models, your coil, your secondary coil, and your primary coil. Based on these equations, the R equal to 1 over number of S, all right? So basically, you know the number of turns, the number of turns in secondary, number of turns in the primary, and you know the conductivity, and you know the dimension. So basically, you can just key in and extract out this data very easily, right? By spreadsheet or by calculator. So you can import that inside there, and you can now you actually calculate the capacitor. So based on the capacitance, right, we are using Maxwell to do it. So Maxwell, basically what you require is you require your geometry. Basically you have your geometry, you know your material, you can put everything inside the 3D models and just solve it in magnetic solver. So when this magnetic solver, after you solve the magnetic solver, you can extract out your L1, L2, and your K. All right. Then for all this, right, data, you can actually extract CP and CS, which is the capacitor, series capacitor, and the parallel capacitor in your primary and your secondary. Okay, so in that case, right, just hold on, sorry. Okay, in that case, right, you actually, can extract out this and key into a circuit. Okay. So if you see this, right, this is just a simple calculation that you need to create your circuit level simulations. Then you can actually put everything inside there, all right? Your rectifier. Now, this is a very good example for a HV vehicle. All right, you can see here we have motor, we have inverter, we have battery. So it's a battery charge simulation with wireless power supply. So we can actually come up with all this circuitry inside Simplora. We have a low frequency, actually is we have a circuit tool called Simplora to actually couple together with the Maxwell. So we have rectifier circuit, we have inverter, we have controller as well. Some of this block that you might not have, like some of these ICs or some of this part, it might be controlled by ICs, right? That you do not have that type of, you don't have that IC chip to put into your circuit, right? What you can do, you can have a controller. You can build a controller like a digital controller, which 1 and 0 to on and off your rectifier. In terms of powering up your charging up your battery. All right, so basically you can do that by using the controller, and you have a battery on the other side, and basically we have the wireless power transfer that simulate in your Maxwell. So basically you can put them together and you can you can use a control circuit that you created in Simplora, right? And actually control your Maxwell coil, okay? So this is more like a system simulations that we can create. So what is required, all right, for the couple system simulation? Basically, the environment is very easy. It's easy to use, right? We are making it very easy for the user to actually to put everything together in a system simulation, right? And of course, these are all linked between your circuit and your model in Maxwell or in HFSS, right? All the parameters that you set up in circuit and your Maxwell model or HFS model is linked together. You can use their transfer data between them. All right, so it's called coupled simulations, right? So this how efficient workflow design will enable a simulation-driven product development, which means that by using simulation to drive your product development, all right, it's no longer just device characterization. We are talking about more on a system-based simulations now. So if you see here, right, I split the chart, and basically you can see that this is how we differentiate what are the tools that we can use in ANSYS, right? So for the lower frequency, we use Maxwell and Simplora. As I mentioned, Simplora is more low frequency simulator, circuit simulator, right? And HFSS and Nextim is basically more on high frequency, okay? So you might be asking, so there's so many tools, which one there'll be, which means that I need to launch HFSS, I need to launch circuit, Simplora. So it's like I'm going to launch 3 platforms to run all this. No, actually the answer is no. So what it does is, in ANSYS, right, we have this called electronics desktop, right? In short, it's AETD, right? So what it does is basically is a single platform. If you see the below, right, when you launch, right, you can see that all the icons are there. So you can actually couple them together in a single platform, all right, basically. And you can actually couple to mechanical as well, because you understand that when your prolonged charges of your coil, right, your coil might be heated up and it come deformations, right, basically, and it can be there can be breakdown on the coil, and we can actually couple into mechanical and see the stress level and thermal efficiency of that coil. So this is, everything will be in a single environment, right? So I'll be focused more on the example for EV, because EV actually is a more, I would say there's a bigger applications, right? Based on whatever you see, charging of this mobile and all that. These are, I think this is already, I would say that it's very matured simulation or very matured product, because the gap is very near, which means that when you do a wireless charging of your mobile phone, right, it has to be very near to the receiver, right? So basically for this case, right, is slightly different, right? So what happened is for EV, right, it's basically inductive type, okay? And you can see that we have secondary coil on the vehicle itself. In the vehicle, we have battery, rectifier chargers, and all that stuff. We can actually simulate that in, as I show you in Simplora. And we have also have the primary coil, which is actually the transmitter, all right, to transmit the source into the secondary coil, all right? And this is basically we are using Simplora and Maxwell. Right, for this case, right, I have put in a little bit of effort to show you that even putting in Simplora and Maxwell, right, we can also couple the Maxwell into the HFSS to see the overall dimension, overall car dimension, right, and how the radiation been distributed inside your car base, right, which is very useful because we need to know what are the field simulations, where are the field losses, right, in terms of a bigger profile. Okay, I'll show you in the next few slides. So this is a car, all right. Basically, we can import. You can have, if you have a CAD tools that draw this stuff. A lot of mobile automotive customers that we have, they have all these car models. So we can actually import into HFSS or Maxwell, right, to do the simulations, right. You can see that below that there is a coil, right. That's a wireless coil, and the secondary one is on top, which is connected to the vehicle itself, and the primary one is actually on the base, right, which is connected to your power supply to charge up and to power up that coil to actually do a transfer of as a transmitter to transmit the magnetic source into your secondary coil. Okay, so there's a lot of things that you need to do on this case because there'll be a gap between your vehicle and the base, your secondary and the primary, all right, basically. This is one of the very early simulations that we did for Nissan, all right? I still remember it's Nissan. So basically it's actually a car that is going to be parked in the garage and you can just start to power up and, you know, you can when you reach home or whichever. So basically this is something that we need to take note, that is because your coil and the base, the secondary of the primary, there'll be a lot of variables, right? For a more efficient power transfer, you know, there'll be gaps between them, right? Obviously, okay, and that gap can be a constant, but the sliding distance between them, that means how far away from the secondary and primary is also crucial in order to give a more efficient power transfer. Okay, so all this can be done in simulation to make sure that what is the efficient distance between them, and the slight distance which is the z the y distance between them, to get a more efficient power transfer. Okay, just go into this. As just what I shows now is actually based on a HV applications, which just now there's a few slides showing how to extract all this C and R, right? It's the same thing, right? You have to calculate the coil resistance and plug in all this data into your R1, R2, and CS and CP is basically, you know, to use magnetic Maxwell to actually extract your L and L1 and L2 and your K to actually calculate your CS and CP, which I showed just now, right? So basically I just jump a step and you can see that this is the major thing that we do now. So what I do is there is a shield plate, because on the HV, right, there is always a shield behind there, all right, because you want to shield your source so that your source will be maximized on your coil itself. Okay, so in that case, right, we have a shield plate behind, which is needed to be in the simulations, because how big your shield plate is, how much your shield plate between the secondary and primary is also a crucial parameters. Okay, so the same thing, you actually model this in this 3D models in Maxwell using magnetic solver, and you extract out all this L, C2, CS, and CP. All right, then you run it in Simplora to see the simulation. So this is the same thing, right? What you require is your dimension, is your model that you can create it in maybe in AutoCAD or SolidWorks, that you can import in all these CAD models into Maxwell, and actually assign all these materials and the rest, right? So it's very simple. Material boundary condition that for magnetic solver, right? Then you can actually use that solver to extract out your L1, L2 and calculate your CSCP, right? So now this is just a flow chart to show you what is going on, okay, basically. That's why I mentioned that there's two variables that is very important, the gap between your secondary and your primary. And also the sliding, because you might not be parked properly, your car might not park properly onto the primary, and there might be some efficiency loss between the power transfer. So all this we need to also calculate what is the worst case and what is the best case, right? Basically, then we know that how to optimize the transfer. We want that to be, because we want a full 100% power transfer between the secondary and between the primary and the secondary, right? That's important. Then firstly, we use magnetic, as I say, magnetic, right, to actually calculate the coil, the core LC1 CSCP, all right. Then we use magnetic current to actually calculate the impedance, right? Then we can actually couple to Simplora to do all this circuit driver control design, efficient power factor and the responses, right? Then after we calculate this, right, we can still push back from the circuit itself, right? You have all this, because 3D solver is just a passive solving, right? So you only solve for all the passive variables, parameters. So now you actually in Simplora, you can actually push this all the source outside your circuit, right, into become the input to the 3D models, right? So the 3D model will take on this source that created in your Simplora circuit and back to Maxwell and calculate the eddy current. And you can see what are the fields on the plate. Remember the shield plate, right? We need to know what are the field losses and what are the current losses, eddy current losses on the plate, right? How to minimize that, right? So this is just a solution flow to show you what I'm going to do next. So same thing, I use magnetic, it's keep repeating, but same thing is I'm use the magnetic solver just for the coil only. I extract out L1, L2, and from there I get my C, S, and CP, all right, based on the equation. So basically, and the other thing is from here, right, we also can do a parametric studies, right, on the gap. So which actually we can put different gap dimensions, right, doing a parameterization, right? Then we can see what are the current, right, between the gaps, right, the eddy current between the gaps. You can see that over here, the charge, right, this is the on the left hand side for the y-axis is actually the current, all right. Then on the x-axis is actually the sliding. So the way it slides away from the primary, the secondary sliding away from the primary, how much current is it absorbed into the coil. So these are all very useful information for you to design or for you to analyze the transfer of the power. Then obviously we can plot out some on the gaps itself to see the mutual inductance between them, the L1, 2. So this is important because we know that there are different materials like the linear one and the non-linear materials that have different type of characterization. So basically we can see what are the differences, and we can make a choice on the different type of materials as well. Okay, you can see that the saturation is there, all right, for the non-linear and the linear. Of course, non-linear is based on BH curve that you have. You can input the BH curve that you require for that particular materials. Okay. Then basically, this is to characterize the Tesla, all right. Basically the Tesla is for the magnetic field plot, right? No magnetic saturation basically on the linear part. So we have to see what are the maximum linear that we can go. So in this Maxwell, right, or HFSS, we have something called field calculator, where you can actually input the volume on the surface of the structures and actually calculate the field or the magnetic losses on the surface or in the volume or in the area. So this calculator is very useful so that you can actually calculate in terms of the point, which point is the highest magnetic field for your magnetic flux field, plot, which point is the most maximum or highest and the smallest. So you can actually, based on that field calculator, to calculate in terms of area and volume. All right. Then after this, as I mentioned, we have to know the eddy current on the shield plate. All right. So by simulating them by putting just now the Maxwell magnetic solver model inside the Simplora, we calculate all these sources because you have all the sources to power up this Maxwell. Then we can actually, with this AC field and losses, right, after you simulated in the circuit simulations, we can actually push it back to the model and calculate the eddy current, all right, on using AC, calculate the eddy current on the secondary coil and the primary coil. Okay. So you can see that between the solver, 3D solver and the circuit, right, is actually two ways, right? It's not just one way. You can push it in and push it out and see what is the overall system simulations like. And same thing, all right, on this eddy current, you have all this coil and all that, which is same thing as what you put it into your 3D Maxwell. So what they calculate basically is your AC characteristic of your inductance, the coupled factors, and your core hypothesis field, the shield. All right, that's important. You can see below, you can simulate with shield and no shield. You can see the difference between the magnetic field, right, inside in the 3D models of the coil. So this is just overall. You can see that you can calculate all this AC and frequency domain, and the transient for the time domain, all right, to see what is the switch of this in the AC form, okay, in the Simplora. And from there you can calculate your using you have the input power and output power, because based on the circuitry you know all your input and your output power. You can actually calculate your efficiency, and from there you can even plot a 3D plot that comparing your efficiency, the gap, and the sliding. So it's like a 3D plot where is the maximum point, all right, that you can get on this efficiency, right, based on these two variables, the gap and the sliding. Okay, so from there you will know what is the optimized point that your vehicle need to stop or need to park, how far or how near to the primary of the coil in order to do a power transfer process. So that is just part of it. Basically, we can put in all this, as I said, we can put in all this rectifier, inverter, your controller to control your overall as a system, okay, and with the battery as well, all right, to see how much battery is loading, all right, when you are charging. So basically, you can see that this whole thing can be done in a system matter, in a system simulation in Simplora versus the Maxwell. So last but not least, right, for this case, right, okay, this is a circuit simulations that is a similar slides that we showed just now. All right. So last but not least, we can actually just like I mentioned, right, we can actually put the Maxwell back and do the eddy current, right? Basically, this is what happened. All right. So when you actually push the circuitry back to Maxwell, and all this circuitry actually calculate all the source, right? And it's actually being applied into the 3D models, right? So when you analyze the 3D models, it's different anymore, because before that there's no source, but now there is source based on the circuitry, and you can actually put in your current and you calculate all this core losses, and all this the core hypothesis losses using your current magnitude and the phase, right? So then the same thing, all right, you can also, on the same models, you can just post-process and do the shield for surface losses, all right. Same thing by the current amplitude and the phase, because your current amplitude and the phase is done using the Simplora. Okay, just putting back the current magnitude and phase into Simplora and solve for the, applying all this source into your 3D models, and actually to see what happened inside your 3D models, all right, when there's all this source of power. Okay, then you can see your shield loss, right? Then you can actually plot out the animation to see what is the effect between the distance and the magnetic field. All right, you can see what is the maximum field on certain distance. Right, so this is a very useful plot, because you will know that at this case, if the vehicle is parked slightly off from the distance, right, then you will not get the maximum power transfer, which means that you will take either the doesn't able to charge up your battery, all right, or the charging will be taking a while or a longer time than expected because your power efficiency is not there. All right, same thing. Okay, so this is the slides that I had just now. And the one of the thing that very interesting is not only that we will see just the coil, secondary coil and the primary coil, we want to put this into the real vehicle and see the whole environment. What happened, you know, when your vehicle is in the garage is charging, right? Does it have any magnetic field that actually concern, all right, with your, maybe you have kids and all that, you know, in the garage, and does it does feel is high enough to affect the health conscious about, you know, human being, or maybe some other causing some other EMI issue. All right, so in that case, right, in the Maxwell, right, we can actually, which is this, you know, this model, we can actually plug this model and put it into HFSS. We call it dynamic link. All right, so this link to HFSS with the vehicle, right, basically this model in Maxwell already have all the sources that you already calculate in Simplora, and we are putting these sources and the models into your vehicle, all right, and do few simulations. Okay, so in that case, this mentions that the car vehicle can be just a 2-sheet object or 3D. It's up to you. All right, basically 2D, basically you solve faster, but 3D you solve slower. All right, basically. But if you want to just to see the feel, right, I think 2D is enough. Okay, so in that case, you can see that this is the link now. Okay, you see that the result is mesh and you plug inside there. And what happened is, this is the interesting part. You want to see how is the feel. This is just animation. You can stop the animation and see the maximum point of the field inside the vehicle. All right, so this could be you know, can be some, you know, this charging of this using the wireless coil, right, might not be in the vehicle. It can be in the petrol station, right? In future, maybe the petrol station, there'll be some of this device, and we have all these cars that park there, right? Then the car to car between them, and you have electronic stuff inside your car. So how is this going to affect, you know, we can all this we can do this in the environmental simulations, right? Virtual environmental simulation, to see the magnetic, how high is the magnetic field. Does it does it cause some concern to interrupt your other electronics components inside your vehicle, right? So basically these are some of the things that we can actually put into your simulation and do a more optimized place. Right? So we talk about Maxwell, which is inductive, but we can now I'm trying I have some few slides to talk about high frequency, which is more direct. High frequency is more direct because high frequency is basically just a radiation field, right? And what you want to see is your S parameters and your resonance, because it based on the resonance to transfer at the resonance frequency to transfer the maximum power into from secondary to primary, from primary coil to secondary coil. All right, so this is more direct. Okay, so on this part, right, we have on the resonance type at a higher frequency, we have HFSS and Maxim, right, the circuit. Okay, and it's a very simple, right? It's just an antenna. Basically, it's just an antenna, all right, to transmit and receive. So this is actually a simple structures, a coil, a single coil, right? We have a pawn and all that, so we can actually create a lump elements based on these simulations. So when you do a simulations, what you want to know is the Z, where is your resonance, where is your cutoff point, cutoff frequency, all right? So this is a 30 megahertz, megahertz operating wireless power transfer. All right, so basically the operating frequency is 30 megahertz. Okay, so in that case, right, we were done to see the S point. This is the field that we can plot in 30 megahertz. How the magnetic field and the current field, you know, plot against each other. Then, as I mentioned, right, HFSS actually calculate both magnetic and electric field. Okay, and we can do parameterization between the distance. All right, to see how the field looks like. Okay, how does the S parameter looks like when it's far apart. Okay, so you can see that we can see that the S21, right, there's multiple plot there. This multiple plot is basically the distance between the coil, right, the coil to coil. And from there, you can actually plot the distance. You can see that the second plot, the plot 4, right? The frequency is almost like 31 megahertz, and you can see that you can plot in terms of different distances, right? What is the S21 like? The transfer. S21 is actually the insertion loss. So basically, it's transfer of energy from one point to another. You want to be as low as possible. All right. So basically, at that point is the highest, which is 1.5 mm. I think I'm not sure. I can't remember the figures, but it's 1.4 in terms of distance, right? Then we have a maximum S21. Okay. Then from there, we can actually calculate S21. We can calculate the transfer efficiency. Right. Transfer efficiency basically is the power transfer. Right. How much power can be transferred? Okay. Then we can even rotate rotate the coil to see does it affect, you see the rotation, right? The angle, different angles, right? Then you will see that how much maximum. So this is just a study, the transfer characteristic between the rotated coil and the stationary primary coil. Then these are different phase angle when it rotates, right? So when it rotates to 90 is basically the minimum, all right? So it has to be face to face, right? Basically, okay. Then on this, we can same thing as HFSS, same thing at Maxwell, we can actually put the HFSS into the circuit, and with the inverter circuits, right? We can actually put everything together and run in a circuit simulations, right? Coupled with the 3D models. So you can see that this is the same thing. We have the HFSS antenna coil models inside there with parameterization variables inside the coil. All right, then we can run the skid to control the coil simulations and see what is the waveform and all that stuff. All right, the charging of the waveform for the batteries and all that stuff. Okay. So to conclude, right, I think we for NC Solutions, right, it's a very mature solutions, right. There's some major customers that we have, which I think I don't really convenient to talk about the customers, but we have some major customers that in the automotive, right, are using these solutions for HEV and EV. And one thing is we require full simulations for system level now. Right? We don't just categorize a single device, and we need to put, once your device categorized, properly designed, optimized, and you need to put into system level to actually run as what you see in the real product. Okay, basically. So we support multi-physics, as I mentioned, right? Combined with thermal, structure, and fluid. So basically, in the future, when your car is at the higher temperature, maybe in the summer and all that, or in the winter, then basically it's freezing up, and basically your battery can be a concern. So basically you will see how much power we need to power your battery, right, when it's very low temperature. So all this can be done in a single platform in AETD, right, combining the thermal and structure together. So with this, actually, I completed my presentation and see whether anyone got any questions that you want me to address.
Okay, thank you, Desmond. To the audiences, if you have any questions, please feel free to type it into the Q&A panel.
No questions? There's
Yes,
only two things where you have no questions.
yeah, we have
Any
a question here.
Okay. I didn't see the questions. Can you read out the questions?
Okay. What frequency should be used Maxwell HFSS simulation at?
Okay. To be honest, right, it's not just based on frequency that you're looking at. Okay, for Maxwell, it's basically for low frequency, and for HFSS, it's more for high frequency. All right. So in terms of when you're talking about inductions, right, it's always low frequency, because induction you are working on either magnetic or electrostatic. So magnetic is always just one solver to solve it. All right, so induction is, Maxwell is the best tools for induction type of applications. So when you're talking about antenna resonance, all right, so antenna, all right, you know, you have an antenna maybe 30 megahertz or even lower, right? But there's a distance between them, like your RFID, for example. It's a very good example, RFID. So RFID, basically, if you tap on it, it's based on the distance. It's based on resonance between them, all right? Because it's antenna. Okay, antenna can be, it can be a less than 30 megahertz. It depends on how you design it. All right. Obviously, when you have less frequency, you know, the gap between them has to be lesser. All right. But if you have a high frequency like 2.4, right, it's like 10 meters because of Bluetooth, right? Basically, Bluetooth, right? So you can have back. So in that case, with that type of distance, right, all right, there's a resonance involved because it's antenna. You want to transmit from the receiver to the, you want to transmit from the transmitter to a receiver, right? With the distance, right? And it's radiating, right? So you involve both metrics. That is your electric and magnetic. So you have to use HFSS. So it's actually application based. You know, we don't just talk about frequency. Obviously, frequency, if if you know that it's higher frequency, you need to use HFSS. But you have to base on what your application is, right? Currently, does it answer your questions? Can a normal piece handle the vehicle model simulations that is HFSS? Oh, okay. Well, no, the detail of that vehicles, right, that we are working on, right, is very detailed. So yes, the answer is yes, you need a good resources with HPC to run it, okay? Because it makes sense. If I tell you that, just a normal laptop can solve this big problem, do you believe me? No way, right? Because when you talk about HFSS, right, you are actually doing a FEM machine, all right? Meaning that based on the frequency that you run, all right, let's give an example like 2.4 gig, and your wavelength to mesh the models, right, as a car is just 1 mm, and based on the car, you have the car is like maybe, I don't know, 2 meter long, height of 1.6 meter height. So this complex structures, right, and you want to use HFSS to mesh it, right, your meshing is going to be very dense, all right, in order to get a very good radiation field inside your vehicle, okay? Like you talk about vehicle, it's not just vehicle itself. Maybe you want a human being to sit inside the vehicle, answering some mobile calls, or maybe some passenger open up laptops behind the vehicle to do some simulation, to do some work, and you want to see whether your electrical car, your all these components can affect your electrical car performance, right? There can be a lot of EMI, EMC issue, RFI issue. So basically, with all this type of detailed information that you want to put into a simulations, right? There's no way a simple laptop can, or a simple machine can do that. All right. If some other tools tell you that no, just a simple machine can, I don't know whether you can trust that, because no way, right? Obviously, right? Yeah. So yes, the answer is yes. You need a good resources and HPC to run it. And I also believe that nowadays, right, to access to all this good machine is not that expensive anymore. And not like what I know. I started out this simulation as my simulation career in early 99, right, year 99. The machine is so expensive, and 1 gig of machines is like, it costs like, can be 8,000 Sing dollar and all that stuff. But now it's so cheap, right? Anyway, you get a normal and you get a good machines, right? Basically, you can handle a lot of good simulations.
Here we have another question. What is the maximum frequency that the Maxwell can deal with, and can Maxwell work with HFSS?
Yes, the answer is yeah. I answer your second question first. Maxwell can work with HFSS. As you see just now, where I coupled the models of the Maxwell into HFSS and do a full simulations, right? So the answer is yes. Then to answer your first questions, what is your gray area between the frequency for Maxwell? Well, as I mentioned, right, when your application come to the fact that you require both electric and magnetic type of field to be involved in applications, right, then you are not able to use Maxwell. You should be using HFSS. All right. So the answer is, I don't want to base on frequency to simulate this, because it doesn't make sense. All right. It's always I always like to use what are your applications. If your application involve, we can easily know that your application might not be involving, so just involve one solver, which is capable for Maxwell to do it. Right. We don't need HFSS. All right. Anyway, HFSS we can do as low as frequency as possible, but the Maxwell is actually a static. We can actually do a static simulations, right? And if you ask me, if you really want to ask me what is the best, what are the frequency, I'll say that for Maxwell, right, anything that less than maybe 500 megahertz, right, should be good enough. Anything that more than 500 megahertz and involve radiation field, all right, because radiation field involve both electric and magnetic, then you need to use HFSS. Right.
Okay, because we have limited time, let's answer the last question.
What is the type of solver, right? It's not FBTD, it's FEM, right? We are using frequency domain, finite domain methodology. That's the last question I see there. What type of solver? Yeah.
So for the audiences,
anything else?
Yeah, we have a lot of questions coming up, but I see our time is up, and please feel free to type your question in the questionnaire. I'm going to send you a letter, and if you fill in the questionnaire, you'll also receive the download link for the seminar file. Okay. Thank you for Professor Kittisak and Desmond for today's presentation. And I'll see you next time. Thank you.
Thank you.
Bye-bye.